What's going on, guys? Justin here, and welcome back to our 8th example video following our course on differential equations. Today's video is going to be on applications of first-order differential equations. So let's go ahead and get into our first example. So our first example is a mixing problem, and let me go ahead and read that problem. It says, a 50-gallon tank initially contains 10 gallons of fresh water. At t equals 0, a brine solution containing 1 pound of salt per gallon is poured into the tank at a rate of 4 gallons per minute, while a well-stirred mixture leaves the tank at a rate of 2 gallons per minute. Find the amount of time required for overflow to occur and the amount of salt in the tank at the moment of overflow. So let's go ahead and write out what this problem gives us. So the first thing this problem gives us is the initial volume for the tank. So we're going to write that as V naught. So V naught is equal to initial volume, and that is given to be 10 gallons. And we're also given values for our rate in and our rate out. So we're going to let E represent our rate in. So E equals rate in, and that is written to be 4 gallons per minute. And then we'll let F equal our rate out, and that will be 2 gallons per minute. So we can represent our volume at any given point in time by V naught plus E times T minus F times T. And that equals the volume at any time T. And that's because that is our initial volume plus the rate in minus the rate out. So what we want is when V of T is equal to 50 gallons. So let's go ahead and make all these substitution. We will have 10 plus 4T minus 2t equals 50, which will give us 10 plus 2t equals 50. And from there, it's pretty easy to see that at t equals 20 minutes, we will achieve overflow. So next we want to find the amount of salt in the tank at the moment of overflow. So we know that the concentration of salt can be given by the following equation, where we let Q be the amount of salt at any given time. So the equation for the concentration of salt is just going to be the amount of salt over the volume. So that's going to be Q over that equation we derived earlier, V naught plus ET minus FT. So with this, we can set up the following differential equation. We will have dQ over dt plus F over our volume, V naught plus, let's go ahead and rewrite this as E minus F times T. And that whole thing is going to be times Q is equal to B times E, where we take B to be equal to the salt per gallon of the solution in. So let's go ahead and make our substitutions into this differential equation and solve. We will get dQ over dt plus 2 over 10 plus 2t is equal to 4. And we can see that this is in fact a linear differential equation. And the integrating factor for a linear differential equation will be e to the integral of this part I've underlined in blue here. So e to the power of the integral of 2 over 10 plus 2t dt. And that's going to be equal to e to the natural log of 10 plus 2t, which is of course equal to 10 plus 2t. And that 10 plus 2t is going to be our integrating factor for that differential equation. So we can write 10 plus 2t times dq over dt plus 2q is going to equal 40 plus 8t. And we can rewrite that as the derivative with respect to t of 10 plus 2t times q. And that is, of course, still equal to 40 plus 8t. Now, we've run out of room here, so I'll go ahead and take that to the top and we can finish this off. And so from here, we can simply integrate both sides. So integrating the left-hand side will just cancel out that derivative, and integrating the right-hand side will give us 40t plus 4t squared plus some constant c. And on the left-hand side, we'll be left with 10 plus 2t times q. And so from here, all we have to do is divide by 10 plus 2t to solve for q. So we'll get q is equal to 40t plus 4t squared plus some constant c all over 10 plus 2t. And we can use our initial condition to solve for this constant c. And our initial condition is that at t equals 0, q is also equal to 0. So that means we'll have 0 is equal to, well, that first 40 will go to 0, the second one will go to 0, and then we'll have plus c. That's going to be all over 10, which means, of course, that our constant c is equal to 0. That gives us our final equation for the salt value at any time t. We will have q of t is equal to 40t plus 4t squared all over 10 plus 2t. And we want to know the q at the time of overflow, and the time of overflow is at 2 minutes. So we want q at t equals 20. So let's go ahead and plug that in, and we will have our final value for our salt at overflow. So q at 20 is going to equal 40 times 20 plus 4 times 20 squared all over 10 plus 2t, which is just 50. And once you evaluate that, you will see that q at 20 is equal to 48 pounds of salt. So that finishes this problem off, and let's get into our second example for mixing problems. So now we have our second example for mixing problems, and our second problem says a tank initially holds 100 gallons of brine solution containing 1 pound of salt. At t equals 0, another brine solution containing 1 pound of salt per gallon is poured into the tank at a rate of 3 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. Find the amount of salt in the tank at any time t and the time at which the mixture in the tank contains 2 pounds of salt. So let's lay out what this problem gives us. We have that our initial volume in the tank is V naught is equal to 100 gallons. We have A, which we'll write to be the initial salt in the container, is equal to 1 pound. And we have our B, which is the concentration of salt in the added mixture. And then we are also given our rate in and out, but the rate in and out is the same, so our E and our F are the same, and that is equal to 3 gallons per minute. So we can plug these into the differential equation that we used earlier. So we'll have dq over dt plus, let's see, we'll have 3 over 100 times q is equal to 3, where our ET and FT terms cancel out there in the bottom, and the top remains just F, and the right-hand side is the same. And we will also find the integrating factor for this differential equation the same way that we did before. So our integrating factor mu is equal to e to the integral of our coefficient there, 3 over 100 dt. And that's, of course, going to be equal to e to the power of 3 over 100 times t. But I'm going to go ahead and write that as a decimal so it's a little easier to write out a bunch of times. So we'll have e to the 0.03 t as our integrating factor. So once we multiply that through, we should be able to write this as a derivative with respect to t like we did before. So we'll have e to the 0.03 t times dq over dt. Plus 0.03 q times e to the 0.03 t, and that's going to be equal to 3 times e to the 0.03 t. We can write this left-hand side as the derivative with respect to t of, let's see, what will we get? We'll get q times e to the 0.03. As if you take the derivative of that and use the product rule, you'll get exactly what we have above. And that's still going to be equal to 3e to the 0.03 t. So now we can take the antiderivative of both sides, and on the left-hand side we'll get q times e to the 0.03. And on the right-hand side we will get 100 times e to the 0.03 t. plus some constant c. So now we can divide our E through, and we'll see that we have Q is equal to 100 plus CE to the negative 0.03 T. And so remember, our objective is to find our salt at any time t. So in order to do that, we're going to need to solve for our constant C there. So we know our initial conditions at t equals 0. The amount of salt in the tank is equal to 1 pound, as given by the problem statement. So let's go ahead and plug those in. So we will have 1 is equal to 100 plus C times e to the 0th power, which is of course equal to 1. So that means that our C is going to be equal to negative 99, and our final equation for our salt with respect to time is going to be equal to 100 minus 99 times e to the 0.03 t. So that completes our first objective for this problem. And recall that our second objective is we want to know the time at which the mixture in the tank contains only 2 pounds of salt. So when Q is equal to 2 pounds, we'll need to solve that. So we'll have 2 is equal to 100 minus 99 e to the 0.03 t. So we can subtract that 100 over, and we'll get negative 98. And then we can divide by 99, which is also negative 99, change that to a plus, and we'll get that 98 over 99 is equal to e to the 0.03 t. And then we're going to want to take the natural log of both sides. So we will get the natural log of 98 over 99 is equal to negative 0.03 t. And then all we need to do is divide that over to get that t is equal to 1 over negative 0.03 times the natural log of 98 over 99. Now there may be a simpler form for that, so if you find a simpler way to express that, go ahead and post it in the comments. So our next two problems are population growth and decay problems. So let me go ahead and read number 3 to you guys. We have the population of a certain country is known to increase at a rate proportional to the number of people presently living in the country. If after 2 years the population is doubled, and after 3 years the population is 20,000, estimate the number of people originally living in the country. So we're going to let n equal the number of people at some time t, and n naught is going to be the number of people at t equals 0. And we'll let k be the constant of proportionality. And so by the problem statement, we know that dn over dt is equal to k times n. But we can subtract that kn over to set up a differential equation that we can solve. So we have dn over dt minus kn equals 0. And our this is of course a linear equation just like the ones we solved before. So our integrating factor mu, so our mu will be given as e to the power of the integral of k dt, and that's of course equal to e to the kt. And once we multiply that through, we'll get e to the kt times dn over dt minus k times e to the kt times n equals 0. And I'm not going to go over the solution process for that differential equation, but once you solve it, you'll find that the solution is given by n is equal to c times e to the kt. Now from our initial conditions, we know when t is equal to 0, n is equal to n naught, which means that we can write this as n naught is equal to c times e to the 0th power, which means that our c is equal to n naught, which means we can write our new equation as n equals n naught times e to the kt. And remember that after 2 years, the population had doubled. So at t equals 2, we have that n equals 2 times n naught. So let's go ahead and plug that in. So we'll have 2n naught is equal to n naught times e to the 2k. And we can divide by n naught to get rid of those, and we'll get that 2 is equal to e to the 2k. So we can solve for k here, which will give us 1/2 times the natural log of 2 is equal to k. But that's a lot to write, so I'm going to go ahead and write that in its decimal form, just like before, to make it easier on myself, which is approximately 0.347. So we have this new equation, n is equal to n naught times e to the, well, we have our new value for k, so 0.347 times t. And we can use our next condition, which is that at t equals 3, we know that n is equal to 20,000. So we have 20,000 is equal to n naught times e to the 0.347 times 3. And when you solve that for n naught, you will find that n naught is equal to 7,062, which completes this problem. So let's move on to our fourth and final example, which is also a population growth and decay problem. So number 4 says 5 mice in a stable population of 500 are intentionally infected with a contagious disease to test a theory of epidemic spread that postulates the rate of change in the infected population is proportional to the product of the number of mice who have the disease with the number that are disease free. Assuming the theory is correct, how long will it take half the population to contract the disease? So first of all, I want to say please do not poison a population of mice just to test your mathematical model. But assuming that this model is correct, let's go ahead and let n of t equal the number of diseased mice, so number of sick mice. And we know that at n of 0, the number of sick mice is 5. And we know that there are 500 mice in total. So that means we can write the number of healthy mice as 500 minus n of t. So that's the healthy mice. And k is once again our constant of proportionality. So since we know that they are proportional, we have that dn over dt is equal to kn times 500 minus n. As the theory states that the rate of change in the infected population is proportional to both the number of healthy mice and the number of sick mice. So we can rearrange this to get a linear equation to solve just like we have been. So once you rearrange that, I won't go through all the math, but you can do that on your own for fun. We will get that dn over n times 500 minus n minus k dt is equal to 0. And in fact, this is a separable differential equation. I believe I said linear before. But before we go about solving it, let's do partial fractions on this first term here. So we have 1 over n times 500 minus n. And that is going to be equal to 1 over 500 over n plus 1 over 500 over 500 minus n, and you'll see why this is helpful in a bit. But that allows us to rewrite this first term as 1 over 500 times 1 over n plus 1 over 500 minus n. And we will still have minus k dt is equal to 0. So now we can take the antiderivatives of these terms. So we'll get our 1 over 500 way out in front, and that's going to be times the integral of 1 over n dn plus the integral of 1 over 500 minus n dn. And then we will have minus the integral of k dt, and that's still going to equal 0. And all of these integrals are very easy to evaluate. So what we'll be left with is 1 over 500 times the natural log of the absolute value of n plus the natural log of the absolute value of 500 minus n. And that's going to be minus kt is equal to some constant c. Now I'm going to go ahead and rearrange this so it is easier to look at, and you could potentially solve this for n, but I'm not going to do that because I don't think it's necessary. But once you rearrange it, you will see that the natural log of n over 500 minus n is equal to 500 times c plus kt. And we can exponentiate both sides to get n over 500 minus n is equal to e to the 500 times c plus kt. But we can rewrite that as e to the 500 c times e to the 500 kt. And we'll write this e to the 500c as our new constant c, and we'll be left with n over 500 minus n is equal to c times e to the 500 kt. Now from here we can use our initial conditions to begin solving for some of these unknowns. So we know that at t equals 0, n equals 5. So on the left-hand side we'll have 5 over 495 is equal to c times e to the 0th power, which means that our c is equal to 1 over 99, which means we can rewrite our equation as n over 500 minus n is equal to 1 over 99 times e to the 500 kt. And what we want to find is we want t when n is equal to 250. Well, if n is equal to 250, this left-hand side just becomes 1. So we'll have 1 is equal to 1 over 99 times e to the 500 kt. And once you solve that for t, you will find that t is equal to the natural log of 99 times 1 over 500k, where once again k is the constant of proportionality, and with the given information there is no way to solve that any further. So that finishes this problem off, and that's a good place to stop.